So, yeah, thank you for the introduction and thanks for the invitation. For me, this is very interesting to hear about the combination or a conference about acoustics, because I'm sitting in an office building with a concrete core conditioned building with no acoustic measures at all. So I know about the problems firsthand. So I'm interested in solutions or other topics we hear here. What I'm going to talk about a little bit, I'm trying to give a brief overview about TABS, or Thermal Activated Building Systems, research that's been done during the past years. So you could say approximately 20 years of experience with these buildings. And yeah, there have been a lot of demonstration buildings in research that have been monitored and analyzed in great detail. And I'm trying to give an overview of that research work that's been done. So first of all, if we're talking about TABS system, or thermally activated building systems, I want to point out that it's not just one technology that you can apply to a system. We see it more as part of a process. So we need to have a more holistic approach on buildings, and always starting with the design phase. So first of all, the first step has to be reducing of energy demand for these buildings to make these systems work later on. So we have to look at shading, we have to look at the building envelope, at ventilation and so on. Then have a look into the surroundings or where the building is located. If there are any environmental or sources in the environment that can be accessed, that might be the ambient air that might be in the ground or groundwater, rainwater, but also the building, the thermal mass the building itself has. Then we come to the technical system, so the HVAC equipment. So we have to use the most efficient systems that might be available. So for example, heat pumps, but additionally that can be combined power and heat systems. And we have to take a look about minimizing parasitic consumption for pumps, also optimizing the hydraulic system of these buildings as far as possible. When we've done all this, a last step can be the fractional covering of the remaining loads by renewable energies. But it's important that that has to be somehow a last step. We have to first look at all the other areas before we can trying to bring or compensate the rest of the energy demand by renewables to achieve so-called net zero buildings. So the idea is to have solutions that on the one hand maximize the indoor comfort, because we are not building buildings to save energy, we're building buildings for users, and to provide this good thermal comfort by a minimum of energy use and cost. So in my first slide, I had that expression, low exergy buildings. I'm not sure if everyone is familiar with the expression or the concept of exergy. First thing you might do is when you hear something for the first time, you might Google it, and that's the same. I did it by myself, looking what the definition Wikipedia has. So apparently it's something in thermodynamics that has something to do with energy, the value of energy, and the surroundings, or your environment or the ambient conditions. Clear definition, but what exactly does that mean for for the TABS system? So our heat reservoir that the system is taken into equilibrium with is more or less our conditioned space. So that's the room we are into. And if we hear that the exergy is the system of the maximum useful work possible, and we want to use not much of it, so we have to use something that's very close to our environment. So we have to heat with comparably low temperatures and cool with high temperatures. So using temperature levels that are nearly or very close to the room or the conditions we are at in, the temperatures level in the rooms we are trying to condition. So tap systems, there are several systems known. This is basically an overview. So typically we have, or when we are trying to bring energy to a room, maybe we recall somehow the physics. If we want to do that with very small temperature differences, we need to use a large surface area. So we are activating surface areas. So for example, in surface near conditioning, the concrete core conditioning or even the floor conditioning that can be additionally added by suspended ceiling panels in areas where we have higher loads or we need faster controls for these rooms. And what about the sources we're trying to access? That's one typical source is in the environment, or we're trying to access is geothermal energy that might be surface near ground by using borehole heat exchangers that can be groundwater if it's applicable. So there might be restricted use if you are allowed in that area to extract water from the ground and reject it again. But that can also be rainwater collected in large tanks and then buried into the ground. And the other source, of course, is just the ambient air that can either be directly used by ventilation systems, so either free or mechanical ventilation, for example, for night cooling, but also with cooling towers, so cooling a water-driven system or water-based system with rejecting the heat to the air, typically to cooler night air overnight. So for different cooling systems, we set up a simulation study coming, this is a laser pointer, comparing different concepts, starting with very basic, simple, free ventilated systems to hybrid or forced mechanical ventilation, to systems with active cooling, for example, fan coils, coming to these taps systems, so where surface part of the construction is activated and either used or accessing an environmental sink, for example, boreholes, and if needed, an additional compression chiller. These different concepts were taken into simulation, thermal simulation, dynamic. Now I've got whatever, you know what I mean. The results for Central Europe, we see. So we're taking these different systems into this thermal simulation and looking if under which conditions a good thermal indoor comfort can be achieved using the different systems. And we see in most of Central Europe, we're good with either night ventilation or even these, or especially these taps systems. So in the most of Central Europe, or in a wide variety in European countries, these systems can be used to achieve a good indoor thermal comfort. Only if you are going to areas with just higher ambient temperatures, typically in the south, then you have to add additional cooling systems like fan coils or compression chillers, or in combination with compression chillers in combination with fan coils. So for the from the theory to reality, as I said before, thermally activated systems, there are a variety of different buildings going back to the early 90s where this has been established or used. Several of these buildings are demonstration buildings in research programs, so they were during the design phase and later on during the operation, they were very closely monitored and analyzed. we measured several of these buildings and trying to compare or rate these buildings and doing a performance analysis to see what works or where maybe still problems are. And if you want to compare or rate buildings, it's very important that you have clearly that you define specific boundary conditions or balance boundaries, so you are really able to compare apples to apples, to compare different concepts and compare different buildings. So we came up with, let's say, 4-stage balances for these systems. The first one is the balance around the environmental or the heat source, sink or source, taking into account the thermal energy that's taken from the source and the electric energy that's used to utilize the source, so basically for pumps. In the next step, we are taking into account heat pumps or compression chillers, so the auxiliary energy that's needed typically for the compressors to shift the temperature level. In the next boundary, the main distribution and the buffer storage is included. And finally, the whole system is so from the sink to the rooms. So for the distribution and delivery of heat and cold is measured and rated. And the amount of thermal energy that's always from one boundary to the next is measured from one boundary to the next one, divided by the amount of electric energy that's used, is giving us the seasonal performance factor of these systems. So we're able to compare different buildings, different concepts, always using the same boundaries. Now, these 4 boundary levels for 2 buildings compared for during the heating season, so using a heat pump for supplying heat. So when we are taking the heat from our environmental sources, we have to shift or to the temperature level to use it for space heating, so typically done by heat pumps. We see a decrease, or this is on this graphs on the left-hand side, the amount of energy is shown for thermal energy and for electric energy, and on the right-hand side it's the seasonal performance factor. So we see a decrease of performance, of course, from the step from boundary 1 to boundary 2. That's clearly because that's where the heat pump jumps in. So we need, of course, a specific amount of electric energy for the temperature rise of the heat pump. But still, the seasonal performance factor can decrease even more because more and more electric energy comes into, we have to take into account. So ending up or starting with, of course, a high seasonal performance factor from just looking at the source, we end up with a seasonal performance factor quite lower. Maybe it's a bit difficult, or you can compare this to the COP, so the coefficient of performance of heat pump systems, which the manufacturers typically give, because that's just taken into account the heat pump itself and not all the auxiliary energy that's needed. So, but having just 2 minutes left, I'm trying to wrap it up a little bit faster. The same evaluation we did for cooling. Same story, we see a decrease coming from boundary 1 to boundary 4, basically because of more and more pumps or auxiliary energy has to be or is taken into account. So it's typically it's a question of hydraulics and how they are designed, that we lose efficiency from the source to the rooms. More detailed analysis of these of different systems, I think I can skip that. Coming to a first conclusion, we see excellent energy values for these buildings, so way below 100 kilowatt hours primary energy per square meter in year in these demonstration buildings. That's including heating, cooling, ventilation, and lighting. One very important thing, what we found in nearly all of these buildings, that an accompanying commissioning is necessary during the first years, because typically these systems are not behaving the way they are planned from commissioning on or from day one on. So we have to measure and rate these systems during at least the first year, or even better, continuously. And I mean, about thermal comfort, there's a lot of things has been said already, so I can cut that short. Of course, as I said in the beginning, I've talked a lot about energy, so the energy demand for heating and cooling and efficiency, but of course we have to look at the occupant and the thermal comfort as well. So maximizing this triangular is the way we have to go. And rating the thermal comfort, I don't think I have to, or we'll cut that short. So that's been done as well, and I can second the fact that it's necessary to use, or it makes more sense to use an adaptive comfort model, because that's what we've seen a good correlation in doing user surveys when we look at measured values from these systems. Yeah, and basically maybe one last slide, because that's what I think what sums it up pretty good. When we look at buildings, how we built them in the past, I mean, it's basically very simple, but just by burning something, and then it tends to be more and more, we stuff more and more technology in them to make them somehow habitable. And that's more or less the thing we have to look for in the future, making simpler buildings, but doing more effort in planning and designing. Yes, thank you.